I'm Brooke.
I'm Erin.
And I'm Emily, and this is the light and atomic emission spectrum in quantum mechanics.
Nature of light. Isaac Newton tried to explain the behavior of light, but light consists of waves. Amplitude is the wave's height of 0 to the crest. The wavelength is the distance between the crests. Frequency is the number of wave cycles to pass a given point in a unit of time. SI unit of cycle unit is hertz. C is constant speed of light. As the wavelengths increase, frequency decreases. Electromagnetic radiation includes radio waves, microwaves, infrared waves, visible light, ultraviolet waves, X-rays, and gamma rays. These travel at a speed of 2.998 times 10 to the 8th power meters per second. When sunlight passes through a prism, the different wavelengths separate into a spectrum of colors, aka the rainbow.
Atomic emission spectra. When an electric current passes through a gaseous element or through the vapor of a liquid or solid element, the electrons of the atom are energized. This energy causes them to emit light. When atoms absorb energy, their electrons move to higher energy levels. These electrons lose energy by emitting light when they return to lower energy levels. The wavelengths of spectral lines are characteristics of the element and make up the atomic emission spectrum of the element. Each spectral line in an atomic emission spectrum of an element corresponds to exactly one wavelength of light emitted by the electrons of that element. The atomic emission spectrum is like a fingerprint. No two elements have the same atomic emission spectrum.
The quantum concept and photons. The atomic emission spectrum of an element should be continuous. In 1900s, Max Planck was trying to explain the color change of an object when it is heated black, red, yellow, and white as it gets hotter. He discovered that he could explain the change by assuming that energy changes in small discrete units, or quanta. The constant that has a value of 6.626 times 10 to the negative 34th joules times S is called Planck's constant. A small energy change involves low-frequency radiation. A large energy change involves high-frequency radiation.
The photoelectric effect. In 1905, Albert Einstein used Planck's quantum theory to explain the photoelectric effect. Electrons are ejected when light shines on a metal. Not every light causes this effect. To explain it, Einstein said that the light could be described as a quanta of energy that behaves as if they are particles. Light quanta are called photons. The energy of photons is quantized by using E equals hb. All photons in a beam of a monochromatic light have the same energy. If the frequency is low, then the electrons will not be ejected. Light has both wave-like and particle-like properties.
An explanation of atomic spectra. Bohr applied quantum theory to electron energy levels to explain the atomic emission spectrum of hydrogen. His model explained why the spectrum consists of specific frequencies of light and predicted specific values that agreed with the results. When the lone electron in the Bohr model is at its lowest possible energy, it's in ground state. In the ground state, the principal quantum number is 1. When the atom absorbs energy, the excited state is n equals 2, 3, 4, 5, 6, and so on. Light is emitted when it drops back to a lower energy level. The light emitted when moving from low to high is proportional to the energy change of the electron. The lines at the ultraviolet end of the spectrum is the Lyman series. It results from transitioning from a higher energy level to the lowest energy level, n equals 1. The lines in the visible section of the spectrum are the Balmer series. The result from the transitioning from a higher energy level to a lower energy level, n equals 2. This is a smaller change in electron energy. Transitioning to n equals 3 are the Paskin series, the infrared range. As the value of n goes up, the line becomes more closely spaced because energy levels are closer together. The Bohr model only explained the qualities of hydrogen, not the emission spectra of atoms with more than one electron. It did not help to understand how atoms bonded to form molecules. It was eventually replaced with the quantum mechanical model light and atomic emission spectrum.
Quantum mechanics. Wavelength beams of electrons are useful in viewing objects that can't be viewed by a regular microscope. Classical mechanics adequately describes the motions of the bodies much larger than atoms, while quantum mechanics describes the motions of subatomic particles and atoms as waves. The Heisenberg uncertainty principle states that it is impossible to know both the velocity and position of the particles at the same time.
Thanks for watching Light and Atomic Emission Spectrum in Quantum Mechanics by Emily Jackson, Brooke Foster, and Erin McGuire, Period A.